Let's take a look at the traces and representations of the Hecke algebra. The representation theory of the Hecke algebra is closely related to the representation theory of the symmetric group, or if you like, the group algebra of the symmetric group. Every representation, let's say rho Q, from the Hecke algebra to D by D matrices with entries in this ring of Laurent polynomials and root Q. Specializes at root Q equals 1 to a representation rho from the group algebra, the symmetric group, to D by D matrices with integer entries. Now we define the trace space of the Hecke algebra just like we do for the symmetric group. So these are all the linear z root q 1 over root q linear functions from the Hecke algebra to z root q 1 over root q, which satisfy so the functions theta q, which satisfy theta q of gh equals theta q of hg. So when we apply it to a product, it doesn't matter which order we apply it to. So the dimension of the trace space of the Hecke algebra equals the dimension of the trace space of Sn, which is the number of partitions of n. Furthermore, every trace theta q specializes, even if it's not the character of a representation, specializes at root q equals 1. To a symmetric group trace. Two important traces are the Hecke algebra analog of the sign and trivial characters. So the sign is defined to be the same thing as the sign in the symmetric group. So the sign of TW is -1 to the length of W. So there's no Q's in that one. But the trivial character, the Q trivial character, maps every generator to Q. So it maps TW to Q to the length of W. The bases of the trace space correspond to bases of the trace space of the symmetric group. So we have irreducible characters. We have induced trivial characters. And we have induced sign characters. Where induction means almost the same thing in the symmetric group. So the induced trivial character eta q lambda is the trivial character induced from a Young subalgebra, the Hecke algebra, up to the whole Hecke algebra. And the induced sign character equals the Q sign character induced from this Young subalgebra to the whole Hecke algebra. Where H lambda Q, this Young subalgebra, is isomorphic to H lambda 1 Q cross H lambda 2 Q, etc. And it's equal to the subalgebra of HNQ generated by all of the generators except, so let's write TSI through TSN minus 1, except for T sub S lambda 1, T sub S lambda 2, etc., up to T sub S n minus lambda L. So the set of generators we're taking out corresponds to the generators we would take out to form a Young subgroup of the symmetric group. So for example, H521 sits inside of H8, and this is the subalgebra generated by TS1 through TS7, except for TS5 and TS7. Now there are no really nice formulas for any evaluation theta q lambda of TW that hold for all lambda partition of n and all W in the symmetric group. I'm thinking of theta lambda q as lambda varies over partitions of n as a basis for the trace space of the Hecke algebra. So not for induced sign characters, induced trivial characters. Definitely not irreducible characters, because if we knew a nice formula for evaluating these things, we could just plug in q equals 1 and we would get a nice formula for irreducible characters of the symmetric group. So these traces are all characters. We don't have nice formulas for evaluating those or for the non-character traces. The q power sum trace, the q monomial trace, or the q forgotten trace. Now there is a q Murnaghan-Nakayama algorithm. For computing each irreducible character of each basis element of the Hecke algebra. But it is awful in the sense that it's a sum of signed powers of q, some positive, some negative, and they're going to cancel out in the middle of the algorithm. And as if that weren't bad enough, and it only works for W of minimum length in its conjugacy class, in its Sn conjugacy class. So if we have V in the conjugacy class of W, but not minimal, then we have to apply a second algorithm to the evaluation of TW. So we do this for the minimum length conjugacy class representative first, and then from that we can obtain chi lambda q of TV. So we've got one awful algorithm, then we have to tack another algorithm onto the end of it. Now, as I implied, we have a basis we have bases chi lambda q, eta lambda q, epsilon lambda q, psi lambda q, phi lambda q, gamma lambda q, corresponding to, so these are Hecke algebra trace space bases. These correspond to the symmetric group trace space bases. Chi lambda, eta lambda, epsilon lambda, psi lambda, phi lambda, and gamma lambda. And these are all related to each other by the same transition matrices that relate the trace space bases of the symmetric group. So these are related to each other by the same bases. Maybe I shouldn't say these. So Hecke algebra trace space bases are related to each other by the same bases that relate symmetric group trace space bases and symmetric function, homogeneous degree and symmetric function bases. So if we have S lambda equals the sum of Koska number K lambda mu M mu, then well, we know that this implies that we have chi lambda as a character being a sum of K lambda mu phi mu. That's the monomial trace. And then we also have chi lambda q being equal to a sum of Koska numbers phi mu q. So these functions are related to each other just the same way that the trace space bases are related to each other for the symmetric group. Also, we have a Q-Frobenius characteristic map that relates a symmetric function basis to each Hecke algebra trace space basis, which is basically the regular characteristic function where we erase Q. So let's define the Q-Frobenius characteristic map CHQ from the trace space of the Hecke algebra to homogeneous degree and symmetric functions by taking a function theta q and mapping it to 1 over n factorial, the sum over all permutations in the symmetric group, theta of w without the q, P sub cycle type of W. So basically the same thing we would do if there were no Q here. We just erase the Q from the right hand side. Now these three characters of the Hecke algebra trace space, well, these three traces are characters. These three traces are not characters. And again, what it takes to be a character is that we need something to be a non-negative integer linear combination of the irreducible characters. So the traces in the Hecke algebra trace space, which are Hecke algebra characters, are precisely the non-negative integer linear combinations of the irreducible characters. Now, since we don't have nice formulas for the trace evaluations for the Hecke algebra traces, it's natural to ask about generating functions. There are Q analogs of the immanent generating functions. These belong to a non-commutative ring in variables x11 through xnn. I'll say more about that in another video. Then we have the symmetric generating functions. So we also can extend the definition of y of g, the homogeneous degree n symmetric function that records different trace evaluations. Here I'm thinking of g as an element in the group algebra, the symmetric group. Now we don't want this to be a symmetric group with just integer coefficients because we want to remember character evaluations that might be polynomials in Q. They won't have any root Q or 1 over root Q's in them. The characters and traces are all going to give us polynomials in Q. So this is going to be a symmetric function with coefficients that are Laurent polynomials in Q with integer coefficients. And that definition is sort of the most straightforward generalization we can think of. So we define yq of g to be the sum over all partitions of n epsilon lambda q of g times m lambda. So next to m lambda we put the induced sign character indexed by lambda. And again, if we can find a combinatorial object in which this evaluation counts something, then maybe we can use it to perform other evaluations as well. The end.